Hello everyone. Today we are going to introduce our work, DrivingGaussian. Composite Gaussian splatting for surrounding dynamic autonomous driving scenes. Modeling intricate 4D scenes from sparse vehicle-mounted sensor data is a challenging task. Real-world driving scenes are large-scale, unbounded, featuring ego vehicle movement and multiple high-speed dynamic objects. The outward captured images exhibit small overlaps among cameras, but substantial gaps across time. The diverse backgrounds and lighting conditions add another layer of complexity to scene representation. Recent attempts with nerve-based methods have fallen short in accurately representing complex driving scenes, particularly those with ego vehicle movement. While 3D Gaussian splatting has emerged as a promising neural representation, it is not applicable enough for modeling unbounded large-scale scenes with multiple dynamic objects at high speed. These fallacies result in low visual quality, blurring on dynamic objects, and poor geometry. In response, we introduced DrivingGaussian, a novel framework representing dynamic autonomous driving scenes with composite 3D Gaussians. Our method excels in reconstructing unbounded, large-scale scenes with multiple high-speed dynamic objects, achieving photorealistic rendering results with precise geometries. Specifically, given surrounding views from multi-camera as input, DrivingGaussian first decomposes the whole scene into static background and dynamic objects. It then constructs the static background sequentially and progressively, utilizing incremental static 3D Gaussians from surrounding multi-camera views. A composite dynamic Gaussian graph is proposed to handle multiple moving objects, individually reconstructing each object and restoring their accurate positions in the driving scenes. The final rendering results are achieved through global rendering via Gaussian splatting. We further introduce LiDAR prior as a better initialization for Gaussians, enhancing scene modeling with greater detail. DrivingGaussian outperforms previous methods in challenging autonomous driving benchmarks, enabling corner case simulation for various downstream tasks. Compared to state-of-the-art, DrivingGaussian achieves optimal performance across all metrics, with photorealistic reconstruction and rendering quality. We also investigate how DrivingGaussian performs in monocular forward driving scenes. Although not specifically designed for monocular scenes, it still shows good adaptability in monocular driving scenes with detail areas. The results also show that DrivingGaussian generates higher quality rendering results with excellent multi-camera and temporal consistency. Even in challenging areas such as traffic cones and lanes, our method achieves pleasant rendering quality. Competitors like Immersive and 3DGS struggle with high-speed moving objects, resulting in unrealistic artifacts, blurring, and disappearance. On the contrary, DrivingGaussian successfully models dynamic objects while maintaining realistic shapes and appearances. Overall, we propose DrivingGaussian, an efficient and effective framework for modeling 4D driving scenes. Thank you very much for viewing this presentation.